Thank you very much for the invitation to speak. I'm humbled by the opportunity. I will talk about work with former postdoc Zach Mohammadi, my current grad student Adam Block, and a former postdoc Dylan Foster. Much of this work is actually due to them, especially Zach. In fact, I'm a theoretician. My slides typically have no pictures, not even pictures. So there are some pictures here. So this is due to Zach. Unfortunately, I don't have any demonstrations. I'm very sorry. I will talk about efficient exploration in low-rank MDPs and give kind of a sense of what kind of problems we're trying to tackle on the theoretical front. So my work, just a little bit of a background, I work on mathematical statistics, statistical learning, online prediction, optimization. And in the last about 4 or 5 years, I've been interested in decision-making and reinforcement learning. I still don't understand reinforcement learning, but I guess I understand it a little bit of it. So I've developed a course on reinforcement learning, which I taught for 2 years now, and had written a draft of a book. So I understand it a little bit, but not too much. So if you come from statistics like me, or from machine learning, what is the simplest model? Well, of course, it's a linear model. That's the simplest possible model. You model the world as behaving in a linear way. And there's a very simple method, least squares, due to Gauss, 95. This is 1795. And both computation and statistics are somehow easy in this problem. We teach this in mathematical statistics courses for about 5 lectures. There is enough juice to talk about this for 5 lectures, but then we move on to nonlinear models, and of course, things like neural networks are nonlinear and so forth. But once you go to reinforcement learning, somehow this way of thinking no longer works, and this was a kind of eye-opening to me when I saw this. Suppose that you know that the optimal Q star value, so this is the best reward you can achieve in state S on taking action A, and I'm being kind of loose here without really defining this. Suppose you know it's linear, so this object that you want to know, how good is action A in state S? You know it's linear. There are some unknown coefficients theta, as in regression. And there is a known feature map phi, which takes your state and action, think of this as a neural network, fixed neural network, pushes them through the neural network, and output you read, read off the top layer, and that's your feature, right? So there is some fixed feature, you know it, and all you need to know is just to learn the coefficients at the top, very top layer. And it turns out that without further assumptions, there is no efficient method to learn these coefficients. So unless you make further assumptions about the problem, it takes exponential in the dimension of these features to learn these coefficients. Okay, so for someone who comes from statistics, this immediately tells you that so there's something about RL that's really different from the usual machine learning. And of course, we know what it is. It's the problem of exploration, right? And I'm talking about, in particular, about specific version of RL. There are many different versions of RL. I'm talking about the setup where you start, you don't have data, you start collecting data, and you have to balance exploration and exploitation. Okay, so this is a very difficult problem. There are all kinds of different paths you can take. And you don't know which data to collect. So this interactive data collection is an issue. So let me start with an example. This is not something we implemented or ran. This is on Mars. A rover trying to explore the terrain. And the goal is, let's say, to find some resource, water or something. And just to orient ourselves, the states would include the position and velocity, maybe orientation of the rover, the altitude, and so forth. The actions would be moving in the different directions. and the camera orientation to take pictures of the terrain. Of course, actions influence the states, and the feedback that we get is, let's say, raw image pixels. So this is a type of problem that we would like to try to understand from a theoretical point of view. But how can we model this problem? How can we develop methods for this problem? Okay, so exploration here is going around and searching the new, unmapped terrain, and the exploration is needed because, okay, it's kind of obvious. The data are limited. We start from not knowing the model, not knowing the environment, and we're trying to collect data. The same problem arises in drug discovery. Okay, you would like to let's say discover new molecules. Actions could be adding different components of this molecule, and the exploration problem is important in personalization, where you might encounter a new person with different characteristics, and you would like to borrow information that you've collected from previous patients to learn something and explore for this particular person. Okay. All right. So what we would like to have is efficient strategies in the sense of both statistics and computation. But especially in terms of statistics, we would like to explore efficiently when the data collection cost of the exploration is high, right? So for the rover, this could be fuel. For genetic examples, this could be a risk of harm and so forth. So we'd like to not just explore at random, but really explore carefully, right? And in a way that that is statistically efficient. Okay. So when people talk about RL being data hungry, well, we would like to develop new methods and understand what makes RL data hungry. Why is it an inherent limitation of the problem? What kind of assumptions do we need to make? Or maybe we just don't have the right algorithms. Maybe we're just not doing the right thing, right? So with Gauss regression, it was trivial, but now the problem is complicated. Okay. All right. The challenge is that efficient exploration is hard in high-dimensional settings, and thankfully, this is the thinking in statistics. What typically saves us in high-dimensional statistical problems is that there is some underlying low-dimensional structure. We'd like to explore such low-dimensional structures in reinforcement learning and figure out a way to take advantage of these low-dimensional structures. So in the example of the rover, even though the high-resolution image might be a very high-dimensional observation, the actual state of the rover is a low-dimensional state. Okay, so hidden and perhaps not known to us is a low-dimensional state, and the observations are high-dimensional. And perhaps we can imagine that there is a map phi, which we don't know, that takes the high-dimensional image and maps it back to the low-dimensional representation. Now, the difficulty with these problems is that if we knew this map phi, if we knew how to decode the high-dimensional observations, then this would drive further exploration in our problem. The issue is that we might not know the right way to decode the high-dimensional observations into low-dimensional features, discover the structure, and this needs to be done at the same time that we explore. That's a chicken and egg problem. This map from high-dimensional observation to low-dimensional representation is known as representation learning, and as I just said, it's a chicken and egg problem because exploration will help with representation learning, while representation learning is needed to explore. Okay, so what I will discuss in a bit is a particular problem where we're able to resolve this chicken and egg problem. So what are the drawbacks of existing methods? There's a lot of empirical work on reinforcement learning, very successful. And part of this is due to these deep RL methods. They're used in practice. And they're good at learning representation, or I guess we don't know whether they're good at learning the right representation, but they're trying to represent well the state. But the exploration part is typically ad hoc. Typically one engineers some kind of bonuses to drive exploration, but we're in the dark as when it comes to the right way to explore. This is true for these well-known methods, TRPO, PPO. But on the other hand, when you come to RL theory, we know how to explore in some very limited number of situations, but typically the results are not computationally efficient. So we'd like to fix this if possible. So our goal is to design sample efficient and practical, computationally efficient exploration methods for RL. So next I will finally discuss the model-free exploration in low-rank MDPs. Now, low-rank MDPs, I'll describe in a second, is really a canonical RL setting with high-dimensional states. So if you're looking for a model, if you're, let's say, coming from statistics and you're happy with high-dimensional statistical models, and you'd like to know what the analog is for RL, arguably this is the low-rank MDP setting. Okay, so let me be a little bit more specific. We will study online episodic RL. So online means that we're repeatedly interacting with the environment. We're deploying, let's say, the robot for an episode with a certain strategy, certain policy. The robot then comes back, we evaluate the data, and then we update the policy. Okay, so that's the online nature of it. And episodic means that we release the agent into the world for an episode of some length. Okay, so here is an episode of length h. X is a state. We take an action A and transition to the next state, and so forth until time h. Okay, and now this repeats over many episodes. Now, the low-rank MDPs refers to the particular way that these transitions are happening. In particular, we assume that the probability transition kernel, this probability density of going from state X and while taking action A into a new state X H plus 1, that has a low dimensional factorization. So this probability distribution has a low dimensional factorization. It looks like this. So you have some map phi star. We're actually not going to know this. We're going to learn this phi star. That's our representation. Think of this as a neural network into which you feed the current state and the action, and the phi star spits out the representation of the state and action. And the probability of transitioning to the new state h plus 1 is just that vector multiplied by another vector, mu star, which depends on the state h xh plus 1. Okay, so this is an inner product in d dimensions, and somehow we would like to leverage the fact that even though there is a continuum of actions and a continuum of states, everything is kind of happening in d dimensions, right? Now, I mentioned before that q star being linear is not enough for to learn, right? There's an impossibility result. This is a stronger assumption, and we'll make one more assumption about this model in that we know a class of functions that contains this phi star. We don't know the phi star, but we know a class of functions that contains it. So for instance, I'm happy to assume that there exists a neural network that will map state actions into this representation, but I don't know it. Okay, so I'm going to have to learn it by doing some kind of optimization. Okay, so the second assumption is what I just said, that we're assuming realizability, that this unknown feature map lives in a known class of functions. what we will do is perform reward-free exploration by computing a policy cover fee. This is one way to do reward-free exploration. We will build what's called a policy cover. Think of this as a database of all possible, a small number of possible policies that let you do whatever you might want to do. Okay, think of it that way. Still informally, but more formally, for any latent state X, we would like to have a policy in this set, in this collection, that approximately maximizes the probability density of reaching the state X. Okay, so it doesn't say that we'll definitely reach it, but it says that if it's reachable by some policy, then by looking at our collection of policies, we're going to be, maybe probability 1/10 of that will be the probability of reaching that state. Okay. It turns out that if you have a policy cover, then you can optimize any reward task you would like. So you can engineer whatever rewards you want, and then there is an efficient method for optimizing that reward function. So a policy cover, okay, I think I'm going to skip the details. This is just saying that the set is a policy cover if it has enough probability of reaching the state. Essentially, that's what this is. So what we have is a new method called volumetric exploration. You can check it out in the paper. That says that under this assumption of realizability, that the feature phi star is an element of our function class. It's a well-specified model. The method returns with high probability a policy cover with a polynomial number of trajectories. Okay. This means that it's relatively efficient. Of course, one can always try to bring down the exponents in this polynomial, but this is a first step and the first result of this form on learning efficiently in this model. So the key features is it's computationally efficient. It's model-free. Does not need to actually model that coefficient mu star on the h+1. It's reward-free, and there are no additional structural assumptions. Okay. So to us, it was surprising that even though linearity is not sufficient to perform efficiently, to learn efficiently in these models, there are some modifications of these assumptions. For instance, knowing these features and assuming realizability and assuming the linearity of the transition kernel, which is sufficient to learn efficiently. Okay, so I think as a field, this is kind of what have been doing in the last 5 or 10 years, kind of thinking about different reasonable assumptions and developing new methods that avoid these impossibility results, which are everywhere in RL. Okay, I'm not going to say too much about the actual algorithm, except that it interleaves exploration. So it interleaves exploration and building this policy cover. It has to resolve this chicken and egg by doing one and then another, switching between exploring and then learning the new representation and then building a policy cover repeatedly. Okay, and several things just came well together, and this is due to really to Zach, who has been working on this. So there is an efficient Frank Wolf method that's used for exploration together with the policy search by dynamic programming from 2003 for policy optimization. There is a certain technique for making sure that we don't care about states that we're not likely to reach anyway, and that's by the use of extended MDPs. And there's a rep-learn method that was developed before for representation learning. Okay, so all of these come together for a polynomial and efficient method. Okay, so I'm going to skip the detail in the interest of time. Let me step back now and just say a couple of words about the kind of the high-level picture. I'm interested in interactive decision making. This is kind of a name we came up with for a class of problems of this form, and episodic RL is an example of it. So interactive decision making is actually more general in some sense. So at each time step, the decision maker, let's say a doctor, receives some context, let's say the medical history of the person, makes a decision which could be a strategy, could be a prescription of a treatment, could be a multi-stage prescription, or could be the whole policy for the robot. And then observe the reward and observe some auxiliary information such as the trajectory and the rewards along the trajectory. Okay? So in the past couple of years, we've been able to, at this level of generality, provide some kind of understanding of what is possible at the level of learnability, at the level of kind of the Wapning-Chernenki's type of result for that you would have for statistical learning, and now there is something similar in this decision-making setting. And I think I will stop here. Thanks.
Thank you so much. We have time for a bunch of questions, so anyone would like to? Yes, please, go to the mic.
Hi, my name is Mahesh, and I'm not sure that this applies directly to what you described, but the very last slide, if you could use that as sort of a, thank you, if you could use that as a summation of everything else that you've said so far, in a sense, if you combine this with the Mars Explorer, let's say the Mars Explorer's mandate is to find water. It also has a mandate for self-preservation. And if it's on the edge of a cliff, for example, and it sees water over there, and at this point, let's say that it goes, the planet goes on the other side and you can't communicate with it for about 2 weeks. It's got two different things, two conflicting things. One is get to the water, the other one is don't jump off the cliff. The same way the doctor over here, going through all of this, the doctor finds that the actual problem is different from what she has been asked to do. She has a decision to make, either do what the government is paying her for or solve the real problem. And so in that case, both the robot and the doctor have to make a decision as to what their actual mandate is. And if they go ahead and change that, do you have any comments on that? For an autonomous system, at least autonomous to some extent, what kind of decision should it make?
Yeah, I don't think I can answer that question at a general level, but this setting, in this setting, we postulate some class of models, and we're assuming one of the models is correct. One of the models is correct. There are some different settings. So for instance, within this picture, we've considered settings where the model is changing over time in a way that is outside of the control of the decision maker. And then the decision maker has to really hedge much more between the possibilities because the model is unknown. The algorithms that come out from this are different, and I'm assuming that if one considers something like what you were suggesting, maybe the decision maker will be more cautious about making some moves that might lead to an unforeseen consequence of that.
All right, do we have? Yes, please.
Thank you very much for the great presentation. I want to ask you, in what ways can you relax the realizability assumptions and also the finiteness of the policy class?
Yes, so thanks. Finiteness of the policy, finiteness of the function class for the feature map is easy to relax. This is kind of standard. Realizability cannot be relaxed here. It heavily relies on the model being well specified. In fact, most of our difficulties in RL, at least to the best of my understanding, is from the loss of realizability. As soon as none of the models in your kind of working class match the reality, everything goes bad, right? So you cannot do regression, things break. One exception here is, I guess, some work that we're doing on having a simulator access. If you can locally simulate the environment, then that can fix some of the misspecification problems. Thank you.
Was there a question there? Sorry.
So your paper is about making reinforcement learning algorithms better at like exploration generally. Is this kind of a technique that you would want to use throughout the like training of the reinforcement learning algorithm, or is it something you'd more want to do at the early stages so you can get a broad view of the like decision space, and then maybe switch to something else for like specializing in like doing a certain technique?
Yeah, that's a great question. So the building of the policy cover actually prepares you for any reward function you might have. So it could be something that you just do when you're faced with a problem for a downstream task before doing the task. That is correct. Yeah.
Okay, thank you.
Thanks.
I think we have time for one more question, if there are any. Yep.
Hi, thanks for a nice talk and nice result. I was just more curious. Leslie talked about compositionality, right? And you're talking about efficient learning. So is there assumptions like compositionality that can make RL more efficient? Are there assumptions that you can define?
I think that's a great direction, and we haven't thought about this. Yeah, I mean, I can imagine different places where compositionality can enter, including these representations. They could be could have different levels, a hierarchy, and that's how we would model these phi maps, right? And then hopefully discover the one that's correct for this task. Yeah, I think it's a good question.